G'day. The purpose of this video is to briefly investigate the application of KVL in AC circuits. So let's quickly define both KVL and AC. Often referred to as KVL, Kirchhoff's voltage law states that the sum of all voltages and voltage drops in a closed loop of an electrical circuit will sum to zero. The term AC refers to alternating current, which produces a voltage with an alternating polarity reversing from positive to negative, giving AC its title. When analysing AC voltages, we must consider both magnitude and phase, so we display it in many forms. It can be displayed as a sinusoid or in complex form, what we know as phasor form. Here we will look at an example of an application of KVL in a simple AC circuit. We have the phasor form of three known voltages and another voltage with unknown magnitude and unknown phase. By KVL, we know that the sum of all the voltages in this loop will be equal to zero. As V4, the unknown, is of opposite polarity to the other voltages, we can equate it to their sum. We now have an equation that we can process to find the unknown voltage. The addition and subtraction of complex numbers is best performed in rectangular form. So, our next step will be to convert voltages 1, 2, and 3 from polar form to rectangular form. Voltage 1 with a magnitude of 10 volts at a phase angle of 0 becomes 9.5 plus J 1.7. Voltage 2 with a magnitude of 20 volts at a phase angle of 60 becomes 10 plus J 17.3. Voltage 3 with a magnitude of 15 volts at a phase angle of 30 becomes 12.2 plus J 8.6. With the voltages in rectangular form, we can now proceed to perform the sum of our voltages to find a value for V4. V4 is equal to the sum of 9.5 plus 10 plus 17 plus J times the sum of 1.7 plus 17.3 plus 8.6. This gives us a value of V4 in rectangular form of 37.1 plus J 27.7. The last step of this problem is to convert our answer back from rectangular form into polar form. Here we have our V4 magnitude and angle in phasor form. V4 is equal to 46.2 volts with a phase angle of 36.8 degrees.